The introduction. Welcome everybody to my presentation. Maybe I will introduce myself shortly. My name is Egbert Barker. I'm professor at the Leibniz University of Hanover at the Institute of Electrotechnology, and I have more than 20 years experience in research and development in the field of induction heating and induction melting processes, and I want to talk about today about some basics of induction melting processes. As you can see along my outline of the talk, first of all, I will give a short introduction, show some industrial background of these technologies, then I will shortly explain the principles of induction melting, the physical principles, in particular the electromagnetic shaping and steering effect, which is very important for this technology. Today we are able to use computer simulation about these processes. I want to show you also some examples of this, and I want to stress a little bit the power balance and the very important efficiency of this technology. Along some classical applications, I will show the different use in industry of this technology, but I will also explain some new developments, and finally I will conclude my talk. The induction melting processes today have many different kinds of applications in industry as well as in research. On the upper left corner you can see the classical mass production applications. These are melting of steel, melting of gray cast iron, melting of non-ferrous materials like aluminum or copper. But not only melting, also casting devices, as you can see below, can be heated by induction technologies. In the upper part, more on the right side of the slide, you will see special applications. One is the melting of high quality materials like nickel superalloys, titanium alloys in so-called cold crucible induction technologies. I will explain later. But also, as you can see on the upper right corner, the crystal growing of silicon is an application field for induction melting, where we are melting polycrystalline crystals to get them solidified to monocrystals. In the area of research and development and material investigations, we can find applications like levitation melting, for example, as you see on the right side. But not only metals can be melted by induction processes, but also glasses, oxides, so-called low conductive materials in the skull melting technology. So you see there are many different multifunctional applications for these technologies. But why industry uses so widespread these induction melting processes? This depends on the requirements they have for their processes. So the industrial process requirements are, for example, the mixing and homogenization of the entire melt. That means homogenization of the temperature, but avoiding of local overheating. But we need a sufficient superheating of the entire melt for casting processes. Sometimes it is necessary to melt in small-sized scrap. Then we need an intensive steering at the melt surface. And always we have to take into account that the ceramics of the furnaces should be not, we have to avoid erosion and clogging of the ceramic lining. And of course, for safety reasons, it's necessary to avoid melt instabilities, splashing, and sometimes, in particular for the vacuum induction melting technologies, we need intensive steering for cleaning or degassing of the melt. And all these requirements can be done or can be fulfilled better by induction melting processes. From physical point of view, as we can see on the later, it's quite multidisciplinary area, the induction melting. But this leads us to the advantages, the technological advantages, which are the main reasons to use induction heating and induction melting. As you can see on this slide, there are many technological advantages like high temperatures we can get, for example, for skull melting processes more than 3,000 degrees, for example. We can have a higher reliability, for example. We can integrate the technologies, the equipment very good in the production lines. But the most important for induction melting is the electromagnetic steering, the electromagnetic shaping, which leads to very high quality of the melt. Also from environmental protection point of view and from energy consumption point of view, we have advantages for these induction processes because we have less environmental impact. We have a low specific energy consumption in comparison with traditional fossil fuel heated processes. We have a very clean atmosphere around the production shop. So there are many advantages which leads us to use this induction technologies. From physical point of view, as I said already, we have a multidisciplinary process. This means, of course, we have to do with electromagnetic fields, for example, which are generated by the high currents. The electromagnetic fields leads us to electromagnetic forces, which gives us a free melt surface shape, as I will explain later. We have heating effects, of course, when we are melting the scrap material, but also we have velocity. That means we have flow fields inside the melt. And sometimes we have a liquid-solid interface, for example, for the cold crucible melting process or for continuous casting processes. And of course, we want to have finally a precise defined alloy composition. And when we are dealing with such processes from simulation, computer simulation point of view, we have to take into account all these nonlinear material properties. So that means this is a quite complicated process, but today we are able to simulate this process and to predict and to design the furnaces as it is needed for the process. The induction melting, of course, is based on induction heating. As explained several times during this EPM Academy, the principle of induction heating is, let me say, very simple. We have the inductor, which is fed by an alternating electric current and is generating the alternating electromagnetic fields. And when this magnetic field is penetrating the metal workpiece, for example the scrap, then we get the eddy currents, which finally leads to the heating up of the material or to melt the material. A very nice example is shown on the right-hand side, where you can see already the advantages which I have explained, that we have a conductless method for heating. We have the energy transfer by the electromagnetic field from the inductor, from the induction coil to the workpiece, to the scrap to be heated. And this gives us a lot of advantages, and we have a direct heating method, so the heat has not to be transferred from the surface to the melt, but it's generated inside the workpiece itself. And of course, also when we are designing induction melting equipment, we have to take into account the very important effect. When we are speaking about induction heating, this is a skin effect, which leads us to a current distribution as shown in this picture, where we have the maximum of the current at the surface and then a decrease to the inner part of the workpiece itself. And this means, of course, also that the heat, the power, is generated mainly in a small thin layer at the surface of the workpiece. And when we are melting material, we have a high power installations, and due to the melt movement, the heat which is generated at the surface of the melt can be distributed homogeneously inside the melt and leads to a homogeneous temperature itself. But the electromagnetic penetration depth, as we know from induction heating, is also one of the key factors when we are speaking of induction melting, when we are designing the furnaces, and it can be calculated very easily, and by the frequency we have the possibility to influence the electromagnetic penetration depth as we want. For induction melting, there are two classical induction furnaces. One is on the left-hand side, the induction crucible furnace, which is mainly used for melting, which has a medium-high efficiency of about, let me say, 80% for steel, and which is running in operating frequencies from line frequencies up to around about several hundred, let us say 1,000 hertz. The induction crucible consists of a ceramic crucible which is surrounded by the inductor. I will explain more in detail on the next slide. On the other hand, we have the induction channel furnace, where we have a furnace vessel which can be very large, and below this vessel there are one or two so-called inductors, and the inductors itself consist of induction coil, a magnetic yoke, and the inductor channel, where the secondary, where the induced current leads to the Joule heat and heated the channel up, and due to the heat transfer, the whole melt can be heated. Also this I will explain later on. This device is mainly used for holding and pouring when we are speaking about iron and steel, but also for melting when we are speaking of non-ferrous metals. Due to its construction, the induction channel furnaces have a comparable high efficiency, about 90%, and the operating frequency is mainly line frequency. The induction crucible, let me say, is the most widespread device for melting of, for induction melting of gray cast iron or steel, but also for non-ferrous metals. It consists of the ceramic crucible, where we can fill in the scrap which has to be melted, and around the crucible we have a cylindrical induction coil, and outside of the induction coil we have magnetic yokes who are guiding the magnetic field outside the furnace, so that we can avoid, of course, the stray fields. And normally there's a steel construction which is the outer part of this furnace. These furnaces can be built in very large units, up to 40 tons, for example, for gray cast iron, and the power rates can be up to 24 megawatts. So they are really high power units. And you can see on this slide, is an example of the real construction of such a medium frequency induction crucible furnace, which runs with a frequency of 250 hertz. And you see this is a furnace for gray cast iron with a capacity of 12 ton and a power of 9.3 megawatt. After melting the whole content, the furnace can be tilled, so it can be casted, the melt, into a container, for example, or in the mold, wherever. And you see also the big water-cooled cables, where we have high currents up to 10,000 amps, and sometimes even more. But this is a very robust and reliable construction. As I said already, the most important, let me say, feature of induction melting is that, of course, besides the heating effect, we get a melt flow. That means we get an intensive melt flow, and also we get a deforming of the free surface. And I would like to explain it, why we get this melt flow along some slides. Here you see a cross-section of the induction crucible furnaces, where the blue color is the induction coil, the brown color should be the ceramic lining, and the red one is the melt. And of course, first of all, we need an inductor current in the induction coil, as it is illustrated here, the inductor current G1. And this inductor current, which of course has to be an AC current, leads to the magnetic field surrounding the induction coil. And as I mentioned, due to the penetration depth, the magnetic field is not penetrating the whole melt, but it's only penetrating mainly in the skin layer. So then only in the skin layer we get an induced eddy current. This is the so-called secondary current, induced current density in the melt, G2, which is mainly in azimuthal direction around the melt, as it is shown in this slide. And now we will get a special effect, which is well known also from electrical drives, electrical motors, for example. These are the Lorentz forces. The electromagnetic force density, or the Lorentz forces, are the result of the current G2 cross the primary magnetic field B, and these forces are mainly acting in radial direction, as you can see in this slide. And due to the inhomogeneous magnetic field distribution and current distribution, this means that the stronger magnetic field we have in the middle part, the middle height of the furnace, and we have lower magnetic field in the lower part and the upper part to the end effect, we got the electromagnetic force density, which is not constant over the height of the crucible, but we have the maximum in the middle part of the furnace. And this electromagnetic forces leads to two effects. One is the shaping of the free surface, because the melt is pressed radial by these electromagnetic forces, and this leads to the shape. This pressing or these forces can also lead to complete levitation of the melt, I will show later. But the other most important effect is that this forces leads to the melt flow pattern, as it is illustrated in this slide. And this melt flow pattern is typically formed in recirculating flow eddies, as you can see here, which guarantee an intensive mixing inside the melt. Of course, this illustration shows only, let me say, the ideal developing of the melt pattern. In reality, it is much more complicated, as we can see here on these slides. Because we have the melt flow with velocities in the powered induction crucible furnace up to 2 meters per second, for example, and we have melt flow, that means we have low viscosity, so we're getting turbulent flows. Turbulent flows means, as you can see here, that beside the average flow we have fluctuations. We have fluctuations here on this slide. These are results of measurements in the melt of low temperature model melt, and you can see that over the time we have intensive fluctuations, which we normally can share in the time average flow, which is mainly for the convective heat and mass transfer, but also in the instationary fluctuations and oscillations, which are mainly responsible for the turbulent heat and mass transfer. And this second one we can describe by the specific kinetic energy of turbulence, which is responsible for the intensive heat and mass exchange, for example, between the upper and the lower part of the furnace. And the computer simulation of such processes should take into account, the numerical models should take into account these situations, so that we are able to simulate the flows when we are investigating and designing the furnace. There are some very important effects. That means the influence of the power and the frequency on the melt movement. With the help of the power and of the current, we have the possibilities to control, for example, the flow. And we know that the velocity, for example, is proportional, directly proportional to the electric current in the induction coil. That means if we have the higher current or we have higher power in the melt, of course we get a higher melt steering, and we get also a higher meniscus shape of the melt. This leads us to some limits by the design, because if the flow velocity is too high, there is a danger of splashing, for example. And the limits are, for example, for the line frequency furnace of 50 Hertz at around 330 kilowatt per ton for gray cast iron melting. But there's a second effect and second influence. This is the frequency. That means with the help of the frequency, we can reduce the velocity and we can reduce the height of the meniscus as shown in these formulas. So if we use higher frequency for the same power, we have the reduced melt flow. And this is the reason that today we are not using mainly line frequency furnaces, but we are using medium frequency furnaces which are running at 200 or 300 Hertz, for example, because in this case we can run them with higher power up to 800 or 1000 kilowatts per ton, and this gives us a higher production rate. The meniscus shape and of course the melt pattern are also depending on the filling level. So if we need, for example, a pronounced meniscus as shown on the left hand side, we have to reduce the filling level because then we get a higher pressure, magnetic pressure. For example, if we want to do some alloying, if the furnace is completely filled or overfilled, then the meniscus shape, of course, is not so pronounced. For the process simulation, you can see here we have to solve, of course, the mathematical equations behind these processes. I only want to show this, how it could be coupled. For example, on the left-hand side, we have the electromagnetic part of our simulation. On the right-hand side, we have the flow simulation. And of course, we have to couple them both in order to take into account the deformation of the flow field on the meniscus shape, for example, and in order to take into account the transient, the instationary effect of the flow field. But I don't want to go here more in details. For the most interesting, from scientific point of view, interesting problem for the simulation of such processes, of course, is the simulation of the turbulent flow. That means we have fluid dynamic problems where we are using today different turbulence models. The classical one, like K-epsilon model, very sophisticated one, like direct numerical simulation for very small scales, not for industrial use, and since around more than 10 years, now we are able to use the so-called large eddy simulation, which gives us a realistic, transient picture how the flow is, how the heat and mass transfer is inside such furnaces. This is in principle a combination of both of K-epsilon model and numerical simulation model. And therefore, today with computer simulation, we are able to simulate the processes very precisely. An example is shown here. This is induction crucible furnace again, where you can see on the right-hand side the typical time average flow pattern with the two recirculating flows. This is industrial unit. You see that means also these industrial equipment can be simulated. But more interesting is if we have a look to the transient case, that means the very symmetric flow pattern is disturbed and we have a high turbulences, which is particular in the cross-section of the transient melt flow. We can observe that there is an upper flow, a downwards flow, and this leads us to a very intensive mixing inside this device, which leads to a very homogeneous material. One word about electrical efficiency of induction crucible furnaces. As it's known from theory, the efficiency, of course, depends on the material which should be melted. So in case of steel or iron, we have always a better efficiency than in case of copper or aluminum, for example. But we have also to take into account, of course, the diameter of the melt to the penetration depth, or the diameter of the pieces of the scrap we want to melt in ratio of the penetration depth. And you see that we need a certain frequency in order to get a low penetration depth when we want to get a higher efficiency. And that's why the second reason that today medium frequency furnaces are used, several hundred hertz are used instead of line frequencies, in order to get a higher efficiency when we want to melt very small size scrap, when we want to start the empty furnace filled up with small size scrap and to want to use the so-called batch process, not the process with the yield which was used in former times. This is the second reason for this. Here is an example for the power balance and the energy balance of the induction crucible furnace for melting of gray cast iron. As you can see here on the right hand side, we need at least around about 390 kilowatt hours per ton. This is the enthalpy, and along this diagram you see we have different losses, heat losses for example, furnace construction losses, but still now the main losses are in the induction coil itself. These are electrical losses due to the high current, some losses in the capacitor bars and the converter, so that we in this, for this example, get an overall efficiency of 75%, so an overall specific energy demand of around 520 kilowatt hours per ton. The second device, or the second induction melting furnace which is used in industry, is the so-called induction channel furnace, which where the construction is quite different from the induction crucible furnace. As I said, we have a furnace vessel which can be very huge and can fill up to more than 100 tons, for example, of melting for gray cast iron. And below this vessel we have a so-called inductor, which consists of an induction coil, and here we have a magnetic yoke for the field guiding, and we have the inductor channel where the current is induced, as illustrated on the right-hand side, where you can see the primary current in the induction coil and the loop of the secondary current through the channel itself. So the heat is only generated in the channel, and the Lorentz forces also act only in the channel, and therefore the heat transport from the inductor channel to the furnace vessel is very important to avoid an overheating of the channel itself, and this was investigated very intensively in the last years, also with the help of computer simulation. Like you can see here as an example, the model of the electromagnetic part of this furnace. That means the induction coil, the iron yoke, the channel itself and throat, and on the right-hand side, the fluid dynamic model, which takes, of course, into account the complete furnace. And these models give us a better understanding what happens itself inside the channel and how the heat transfer goes. So we have no big intensive integral flow through the channel, but we have an intensive flow in the cross-section of the channel, coming from the electromagnetic forces, as you can see here on the left-hand side, which are also radial pressing or radial acting on the melt inside the channel, and this leads also to two recirculated flow eddies, like you can see on the right-hand side. These are the flow eddies, which are very intensive, and these flow eddies, which consist of two eddies, are around the whole channel, and these results are also have been validated by measurements. And here you can see, if we look to the complete channel, that we found these flow eddies along the whole channel itself, and the heat and mass transfer between this very turbulent flow eddies. This is the reason for the good operation behavior, so for the heat transport from the channel itself up to the furnace bath, which is very important for the operation of such a induction channel furnace. And these are results of 3D simulations we have done. And as you can see here, this is the channel of a double loop induction channel furnace for melting of copper after solidification of the melt and removing the ceramic lining in the channel. And there you can find also the solidified structures, where you can see that there have been very intensive flow eddies, which of course have made this characteristic structure in the lining, which we can find then in the solidified copper after taking away the lining. That shows us that our simulations are quite in good agreement with the realistic situation. And due to this very intensive smell steering and this instability we have inside this channel, we get a non-symmetric situation of the temperature distribution, as you can see here on the right-hand side of these pictures. And this shows us that we have an influence by designing the channel on the temperature distribution in the channel itself. And we can also calculate, for example, the overheating temperature, which should be, of course, limited due to the stability of the ceramic lining itself. Let's come to another application which is used in industry beside the classical one for mass production. This is induction furnace with cold crucible, which is used for the melting of titanium, for example, or the melting of nickel superalloys. As you can see here, in this case we don't have a ceramic crucible, but we have a water-cooled copper crucible, which is slitted in order to realize a kind of electromagnetic transparency. We have the inductor around this crucible, and the crucible itself and the bottom, of course, is very intensive water-cooled. In this case, the electromagnetic forces are very, very strong, so we get a well-pronounced meniscus shape, and the melt only has a contact on the bottom of the furnace itself, and that's why this technology is also called semi-levitation technology. This contact with the water-cooled copper, of course, leads to very high heat losses, but on the other side we get a so-called scowl. That means a thin layer of solidified material, which has to be of solidified melt material, and this small thin layer, the scowl, protects the crucible and the wall and the bottom against the high temperatures of the melt, but also protects the melt against impurities. So we can get a very high quality melt, and this device, as I said already, is used for titanium, for example. On the other hand, of course, we have a lower efficiency due to the intensive heat losses and due to the inductor currents which are induced in the water-cooled palisades, in the copper palisades itself. And here you can see a picture of the operation of such a device. The big advantage is that we can realize the melting process itself, the alloying, the overheating and casting in one process steps. And of course we have also this very intensive steering inside the melt caused by the Lorentz forces, and this leads us also a very homogeneous temperature distribution. This is the cold crucible, the furnace. If we are speaking not of melting of metals, but speaking of low conductive material, we can use the so-called skull melting technology. Here there is an example of the skull melting technology where we are using no crucible at all. So that means the crucible is built by the one-turn induction coil. Then this device can be used, for example, for oxides, for glass melting, and during the melting process we also get a skull. That means a thin layer of solidified material at the surface, at the inner surface of the water-cooled inductor. And here we can get very high process temperatures, up to 3000 degrees. We have a very high power density, and the skull protects the water-cooled inductor against the high temperatures of the melt, and also leads to a high purity of the melt and the final product. This is the so-called skull melting technology, which is partly used in industry, but mainly now also in development. And it gives us possibilities for the induction melting of these low conductive materials. And finally, there's a technology which can be used for very small scale melting, which very high purity. This is electromagnetic levitation melting, where we have no contact at all with a crucible. So we use the electromagnetic forces for completely levitating the molten material, So we get high temperatures and high efficiency, and of course also this mixing effect and homogenization effect as well. This application is up to now limited to very small mass, so very small scales. So it is used for precision casting of special alloys, for medicine and dental applications, for example, or for the investigation of new material compositions and for determination of material properties, for example. Because this classical electromagnetic levitation melting is limited, because we have no acting forces at the center of the melt when we are using conventional cylindrical coils, as you can see here in this picture. That is why we have developed at the moment a new setup for electromagnetic levitation melting, which is working with horizontal magnetic fields. These horizontal magnetic fields are generated by two pairs of induction coils with different frequencies. As you can see here in these pictures, there are two pairs of induction coils which are located left and up and down of the molten charge, and they are generating a horizontal magnetic field, and this gives us the future possibility to melt bigger masses or even in the electromagnetic levitation melting process. And here you can see the computer simulation of the melting of 500 grams, for example, and here you see that also in this case we have the typical flow development which we know from induction melting processes. This means we have the typical flow structure, the recirculating flow structure, but we can also see that we have a very flat bottom, that the Lorentz forces are supporting the full bottom of the melt, so we can hopefully increase the mass, and then we can use this device or this technology, this process also for bigger masses of melting. Here you can see how it looks like in reality. We have a very intensive steering, so we have a deforming of the surface, but we have a stable enough situation so that we are able to melt, for example, here 500 grams of the aluminum sample. So this brings me finally to the summary of the induction melting processes. I think I have shown that the melt steering is a very important effect which leads to this melt homogenization, and due to the intensive steering and no local overheating, of course, we have small material losses. This is also important, and we can adjust the alloy composition. As typical for induction heating as well as induction melting processes, of course the temperature can be controlled very exactly. Also the process automatic control is positive, and we get a very high quality products. We can heat up very fast to the intensive power which can be realized, and we have a good energy and control and friendly working conditions. And because we have no burning processes, for example with gas or others, we have a very small emissions at the operation in the plant, let me say. And I have shown that there are some very interesting new future-oriented technologies possible, like the skull melting, for example, and the levitation melting, which are at the moment under development. So I will come to the end of my presentation, and thank you very much for your attention.